what are we looking at in this plot? If positive is the thing that I would like to detect, then an ROC is going to encapsulate all of the relevant error to whether or not you're successfully detecting the class of interest, the class of merit, right? So true positive score, these are the ones that we want to detect. So we could say condition, positive, or we could say gold, standard. And here we have predicted case. So predicted case positive TP, that's handled. That says somebody has cancer, we detected they have cancer, right? So what's the other condition that we're worried about? We're concerned about condition positive, predicted negative, false negative, right? So FN, this column right here, effectively describes everything we're really concerned about, okay? The reason why I say that it doesn't encapsulate all of the error is because, remember, our FP up here is another error type. And what happens is that errors will balance along this axis, right, relative to the spillover from the actual correct classification. So, anything leaves the correct classification axis, spills over to the alternative axis. We are going to say that we are more interested in the false negatives, those that were missed, or the relative miss rate, than we are about those that were brought in, right? These are the ones across the border that got captured by or were amassed by being adjacent to samples that were mixed in with the other class group. So as the space mixes, we start off with some discriminant maybe here, trying to describe the relationship. It drifts over, pushing this way, in order to what? I want to capture these again. These are positive cases. These are what I'm interested in. They didn't get detected, okay? So that means my model is not sensitive enough. They were present, but my model didn't detect them. So when my model isn't sensitive, I'm going to have to move my discriminant boundary over, right? How did we do that? Well, how did we encourage that discriminant boundary to move? What was the idea behind that?
Make it more sensitive.
Well, how did I accomplish it?
Offset through, was it bias or variance?
But it is biased to a certain perspective, right? So what I would say is, let's say in a strict linear discriminant, right? Where do I place the discriminant? Let's assume uniform variance, right? Let's assume uniform prior for one thing, and normal distributions. Where do I place the linear discriminant?
Right in the middle.
Right here? Right in the middle?
Between the two.
Right here?
Yes.
Okay? This is your delta. Okay?
Right.
Now, what happens if I push it forward here? That's a type of biasing, right? I'm going to be adding just a scalar element in order to shift it over. That's all I did. That's all I did, okay? How did I get the system to preference that way? Because we know that this mechanism does not utilize individual data points. There are no individual data points here. So how did we get this to do that? Okay? How did we utilize missed samples in order to characterize this? I can rescale my error, okay? I can make a system that says that the error, right, relative to some coefficient for some system, right, I can have an additive characteristic here of some weight relative to the score typing, right? I could say this is a 1.0 error, right? Anytime that I misclassify something, I'm going to say it's exactly it. I get whatever error it is, I count it as a 1. I can say this is a 1.0 error, right? Relative to that casing. Guess what? These are scored relatively. These are correct. So since these are correct, what happens in that regularization? What happens in the score metric? We said that it is the summation of all values. So the summation of all systems for the error metric such that y is not equal to, or excuse me, y hat not equal to y, but either way, right? What is this? This is a binary. This is 1 or 0. What happens to these? These are non-error. They do equal the target, right? So they're fine. So I'm going to say those are 1.0 error types. You got it right, but also your zeros, okay? So these don't actually factor into error. 0 times 1 doesn't matter, right? But we're going to start off imagining everything is considered equally. Then we're going to look here, we're going to say false negatives are important. Now we're getting 1s, right? Now we're getting 1s. Now we're getting error. Because the implied, right, the inference or predicted output value does not match condition positive or condition negative. This is going to generate error value. So this is any time, in this case, this is any time we have the OR condition, right? Anytime the OR condition occurs. You can actually utilize this with respect to the calculation of the error typing if you want to. But what I'm going to say here is I'm going to apply a weight. This is another metric. This is not a coefficient. This is a way in which I take the error generated here, and I say I could start off by the assumption that each of these relevant errors is considered just an error. They're the same. They're equivalent with respect to one another, right? But I also said beforehand, this balance is established based upon what? It's based upon which error we would be willing to sacrifice in order to minimize the relative error in the previous column. So in order to minimize the summational error of all positive case conditions in the data set, I must sacrifice some true negatives to become false positives, right? These are tribute, okay? They're given up in order to optimize the system because their placement and their preference now being detected as positives is just something we have to deal with. In order to make a model that is sensitive enough in order to have maximization of all condition positive scores. Remember we said condition positive. That's the whole column here for condition positive. In order to maximize condition positive, we are going to have to sacrifice false positive. Now, let's look back at ROC. Do I care about true negative? Yes, sort of. But is true negative somewhat handled in the summation of error, considering the fact that this axis, right, is reflective of all the correctly classified values? Correct, it is. So good TP is going to imply that if I don't have a heavy FN-FP ratio, that TN is also going to be low. There's nothing else to go there. Okay? So I've taken 4 values and I've now reduced it to 2 that I actually care about. That I believe if I balance those 2, that everything else really will fall in place. Since I can't technically control this, other than to maximize this and hope that I minimize this, right? All I can do is crank knobs such that this is minimized relative to maximizing true positive score, yes?
And doing that is varying the threshold of FP and FN, correct? or would that or would that more imply to that?
Not threshold, not threshold. I think you're slightly using, okay. Threshold down here would be comparable to delta, right? So
Okay.
threshold, this would be, right, value less than 0.5.
Okay.
Okay, that would be the threshold. So in the slide that I provided you with, and it says threshold is valued, that's pushed over. But how do I actually get it to push over? Well, I weight this distribution more. What is actually happening to it? This is the cool part. If I put this at 1.5, that means every single error value metric in this localization becomes 1.5. What actually happens to this system? Its magnitude is increased by 1.5 times its original value. Okay? It's more weighty, right? Each individual value has more considered significance with respect to the placement. So the prior, remember pi? You weight pi. All you have to do is weight pi. What happens is it says this one's more important. Since that one's more important, it will push it over until, guess what? I captured all of them. I captured at least almost all of them. They're tiny. There's a tiny little fraction over here that may not get caught on the very edge, right? What happens if I capture all of them, That's where I'm at the very top of the curve, right? What happens? What has happened to the accuracy? True positive rate. True positive rate here, right? It's this. It's the space on this side of the discriminant boundary, right? It stops right here on the old discriminant, okay? These samples in this space, in this overlap region, are going to be falsely considered as negatives. They are positive, right? The values that are here are positives, but they're going to be considered negatives now. By pushing this boundary over, now everything is going to be correctly classified as positive. But as a result, all of the values on this consideration, all the values over here now, right? So this whole space here, you guys see it? This whole space here, if I was to decompose it and look over here. Originally, the boundary is here, right? I push over to try to capture. I'm glad you guys got the text out to make sure everybody got into on the sign-in sheet. I really don't know why you guys are on campus and just skip class. That's always been an interesting element to me. ROC curves characterized with respect to a true positive score and then false positive score, right? So it says, how much am I willing to compromise negatives to turn them into positives to make sure that all of my true positives are captured as positives, right? How much false negative has to be optimized. So false positive rate, FP rate, here, how much do I get captured in that spacing? This is samples that were not positive but now are considered positive in order to make sure that true positives are considered positives rather than FN. So if I minimize FN, that's technically going to be balanced with FP in order to max TP. So this is actually, it's weird. I actually see this graph, you look at it and go, it's a two-dimensional graph. But you're like, yeah, there's like more than 2 dimensions here somehow. Because as that curvature is changing, you're not looking at a flattened curve. You're not looking at a flat curve. You're looking at a temporal curve. This is like the whole thing whenever you're in physics class and you throw the baseball and it's got that dotted line that shows its ballistic trajectory, right? This is the change in the performance of the model relative to each of the conditions that are implied as I adjust the weights to change where the threshold is. If I push it all the way over, I'm at full maximum true positive rate. But what also happens? I also maximize false positive rate. So what ROC is going to do is it's going to allow us to balance this so that we have a reasonable amount of false positives, right? Reasonable false positives. And we're going to say, what is the maximum value of true positive rate that I can get while still having a reasonable minimal value of false positive rate. This is where I say the balance point is actually what you make of it. Okay? You can choose what threshold is admissible for you. You can say, I want to have 93% true positive capture. But that means what? I got to trade off. I got to compromise. This is one of the things that I'm spending more time on it, right? I usually spend a lot of time on people go, okay, yeah, I got it in my head, I got it in my head. If you get this, this is just like the concept of regression, right? The idea of utilizing error metrics to associate the improvement in performance. This is very similar to understanding the limitations of a machine learning system. This might be the pivotal or most foundational concept that is involved with machine learning. You cannot make perfect models. They do not exist. They never will exist. This is fundamental truth. You will never have all the data. You will never have a model that has all perfect data. You will get a model that is as good as you can get with the data you've collected, that is as corrupt and screwed up and bad at life as humans. Okay? Machine learning is not going to improve upon the system that created it. We will not create perfect decision-making systems. There will be no robot that replaces judges because it is totally unbiased, right? It's perfect. It just makes all its decisions based upon purely logical information, okay? If it's making its decisions based upon past judicial legislation, then guess what? It was trained with bad data, and it's going to be a trade-off. It's going to get it wrong a certain amount of the time in order to get it right a certain amount of the time. This sticks with us forever, and like I said, this is one of those illusions that I have to disabuse you guys of. Because of the fact that we have this, what do you call it? I would call it a romanticized notion of AI, right? That it's gonna supersede us, it's gonna surpass us. Okay? Maybe it could, but with the methodologies that we're discussing here, it will not. It will not. As long as it is still trained with data that is being provided to it by a human, as long as that data is still being curated by the flawed and fallistic capacity that we as individuals have, those models will be as broken as we are, okay? We can make some of them that are really good at doing a very few things. Making one that's good at everything does not exist yet, all right? Matter of fact, I would go so far as to say I'm not certain it ever will. But there are ideas that we've come across in life. These are things that have persisted throughout time, where we say, oh, I think I understand the model of how this works. And then later on, we come to a new understanding of the model. Given the current understanding of the systems, given these classical methodologies, a model will only get good, will only be good at detecting either, right? It'll either be sensitive, meaning that it detects all the viruses, right? Or it will be specific, meaning it's really good at detecting that one type of virus that it's designed for. Think about this from the perspective of you guys' training thus far in life. Every time that you spend an hour learning to do something in the computer space, that's 1 hour you haven't spent elsewhere, right? Sport, music, art, right? It truncates you into a direction in life. You become more and more of a specialist and less of a generalist. Humanity actually has that bottlenecking notion. We start off as infinite. Tabula rasa, as it says in the Latin, the blank slate. All right? Start writing, and it's like playing Tetris. You put the blocks in place, and as the blocks fall in place, guess what? It is not an infinite combination anymore. It is now a finite subcombination. Models are the same way. Once the model starts training, once it starts converging to a solution, once it gets good at detecting one type of information and trying to minimize its detection of outside information, it begins to go in a direction. It grows, it learns, and it operates just like an organic learning system in the effect that once it's committed to that process, it can only die and be reborn again and start again, okay? You can't learn everything from all data sets and create a perfect model. If I'm wrong on that at some point in time in life, you guys can definitely come back and tell me. Right now, I'm going to go ahead and state that that is as I learned it, that is as I understand it, And the truth is, if you guys look at the mathematics and the underpinnings of these systems, I believe you'll agree with me on that perspective. Okay, discriminant analysis, we had previously linear discriminants. If I said a quadratic discriminant, what does a quadratic discriminant look like? Well, along these two-dimensional lines, right? Along these systematic two-dimensional lines, I don't really need quadratic discriminants. Why? Well, because on two-dimensional systems, the only way I can separate them is with planar elements. However, if I have, as we said beforehand, these topographical distributions, right, the 3D version of our plot maps, and I go, well, there's a slight asymmetry to this one, right? This one's easy, I can put a straight line through it. But imagine this one, let me go start again, and draw it again here, so you understand what I'm talking about. Imagine this one is more elliptical. Changes the game, right? So now, I used to be able to just put a line through the middle, but now I go, well, the priors are all off. The sigmas in each of these axes are different. So previously, sigmas, right, your standard deviations, your variances from center, and relative magnitude pi prior, right, relatively symmetrical, relatively Gaussian. Now we have slightly non-Gaussian distributions in an off-axis. So one Gaussian distribution in one axis, another Gaussian distribution in the other. A strict line will not work, because now we actually have a non-linearity relationship, because we said previously, if pi was the same in each axis here, right? And let's say here I also have a pi, right? I have a prior characteristic or density characteristic. Well, I have a population per unit space. What does that end up being? That ends up being F for the casing. So I have two F's. I have F and I have F prime. I have one function, one density function that spreads across the width of the distribution, and another density function that spreads across the height. Two different distributions. It's not linear anymore. So instead of using a line, I'm going to have to use a quadratic or a curvature to be able to make the line change relative. The change in the shape of the line is relative to the change in the shape of the density function. Delta F per unit axis changes the quadratic as it moves around the outside of an asymmetrical curvature. Yeah?
When you're showing circles, the non-Gaussian, is there, I'm trying to remember if it starts with an M, that type of distribution?
Oh, there's several of them.
There's
Several of them. You can have a Poisson distribution, you can have a Bernoulli distribution, you can have a Markov distribution, right? Which Markov is, it's not the same as the Markov process. You can also have a systematic binomial. There's well, you have power distributions as well, right? So you have power distributions, you have squares of order and squares of exponentials. But most commonly, we're looking at it in terms of like exponential, normal, and Poisson distributions are amongst the most common, as well as binomial. Geometric distributions, that's where I'm saying power distributions. Geometric are probably the most common because we have a geometry, right? Meaning the distribution changes relative to the axis. So this would effectively be a geometric distribution along two axes, where maybe you have a relationship, a ratio. You say this is the 1.0 axis and this is the 1.25 axis, right? So we can utilize an internal understanding of the way in which the spread changes relative to the directionality. Sometimes these work a little bit better with point plots, but if you understand them as being like a little hill, a little mound, right? The little mound is very tight on this axis, but it's much longer on the other axis, right? It's a rounded, you know those ice cubes you get out of the automatic ice maker, right? They're round on one side and then they're kind of narrow on the other, okay? That's kind of what it looks like in 3 dimensions. Versus just a totally hemispherical distribution or quasi-hemispherical distribution, right? The normal fall of the sombrero on the other side. Sombrero says, I don't need to change it because it's the same. As I change the slope of that discriminant with respect to the delta, what am I changing? If I have two concentric distributions here, what happens is I change the slope of the line that's transecting them. That is the same as whenever I change the surface distributions for the projections, right? So by changing the angle of rotation there, the linear discriminant analysis projection changes the spread, the within class spread and between class spread of the distribution groups. What happens to the within class spread and between class spread of these two distributions as I change the angle of the linear discriminant projection? It's all wonky, okay? You get over here and it's super wide looking from this direction. You get over here and it's super narrow looking from this direction. But oftentimes you'll have to do something kind of weirdly off axis to optimize or maximize these. So I would have to have a line that would do what? Cut into this guy pretty bad in order to be able to make sure I captured everybody across this particular projection axis. So instead of doing that, we're going to increase the projected dimensionality characteristic and allow the system to have a linear discriminant multiplied by or modified by the characteristic of a quadratic operation. So by using that quadratic operation, I'm going to use the transpose of the mean matrix multiplied by the characteristics of the log of the distribution relative to the axis, summary to all the logs of the system. Don't worry about this too much. This one is, when we think about it this way, think about the idea of a line plus the square of another weight, right? X, beta 1 of x1 plus beta 2 of x squared. What happens? It was straight, right? And if I have all the weight on the straight part, I keep straight. If I put some of the weight over on the square part, what happens to it? It starts to turn into a parabola, okay? When we say anytime, this is actually good. This is actually good. So I say anytime I have the beta 1, right, times the first power of x1 plus beta 2, this is my second control, to the second power of x1, I can change this, right? More weight I put on linear keeps it rigid. It goes, it doesn't want to bend, right? But as I keep adding on values of the square characteristic, it becomes more and more parabolic. Strictly linear, strictly parabolic, and the value of the summation somewhere in between. Okay? And the somewhere in between becomes what? Flexible. I can have degrees of curvature, all right? So the degrees of curvature are what being described by the degrees of flexibility for the line we're putting in place. I can have, if I have relative symmetry to these, if it's 1 and 1.1, then I only need a little bit of flex in order to be able to compensate for that. If it's 1 and 37, right, it's a narrow sliver on one side and really long, right, I might need something that has a lot more curvature in order to compensate there. So it's going to go much more strictly toward that quadratic characteristic on the other side. Not strictly characterized by that, but it would be related there. You can see actually the value densities of specific localizations, first being the first power, first order separability of the standard linear discriminant, right? This is the ideal separation surface. This is the core distribution. This is the the linear discriminant analysis, right? I guess you could call it a modified logistic projection. Linear discriminant, and then this quadratic that compensates for an asymmetric density in the distribution of each of those class groups. You notice that this one has more of an ovoid towards this direction, and this one's sort of an ovoid towards that direction. And curvature attempts to try to find a balance between those things and those in two directions simultaneously. So when you guys are doing your quadratic discriminant analysis as part of your lab assignment, right? I think I gave you the option to do to do did I have you guys do quadratics on your own data sets? Okay, so I'm having you guys do quadratics to compare between the first data set that you had. So where you're comparing logistic, LDA, and quadratic, right? And then the last case, these are only the last two things we're going to talk about. So if we have questions on quadratics, you'll get experience in seeing how they work, right? And you can plot relative to each axis the spreads, right? There are variances, so you can see how much the variance affects how strongly the quadratic gets factored into the discriminant analysis. You'll also see that if there's a high asymmetry, that the quadratic will outperform the standard linear model, because that additional flexibility is necessary to encapsulate the underlying process. We haven't really talked about the full impact of nonlinearity, but this is probably the first time we're talking about it. If it's not strictly linear, then a model that allows it some flexibility, that allows it to be able to operate by a small amount of the square, for instance, will allow us to now double optimize. We now have a double optimization problem. How do you do double optimization problems? There's a lot of ways to do it, right? We can minimax, we can max based upon accuracy, we can max based upon error, but oftentimes we're actually maximizing based upon what? Those RC curves, right? We'd be looking at the AUC of the rock curve in order to be able to ideally place the discriminant boundary, or something like it from a metric inside. I can use those ratios as my error metrics, as the methodology by which I'm utilizing to optimize the system. So maximum TP, maximum TN would just be the accuracy metric, and you can train a model just to maximize accuracy. Yes?
Do you know if there's a plot command in R that'll let you simply plot the rock graph based on your...
There's not one built in. There's not one built in.
So you'd have to
Mass
plot
actually,
XY.
okay, I gave you guys the PDF for Mass.
Right.
Mass has a lot of additional functions.
Okay.
And it has the ability to import additional libraries. Search through there for plot library types. I believe ROC. There is a good ROC in the plot library type in Mass. Maybe it's in Cran. Hold on. Let me look.
Okay.
Let me look. I'm not going to speak to that definitively. I believe there is a good plot function in Mass for Rock, but it might be in Cran Core.
Okay.
Cran Core is actually the group that keeps up or maintains R.
Right.
So CRAN group, they are the they have their own library. Cran is a separate library. I believe it is loaded by default with our desktop, but it might just be integrated. Okay. Sometimes people are showing me that they have to go over, and every time they launch our desktop, they have to go over and make sure the packages are running. They have to click the little radio boxes. You can set up your default environment. So if you go underneath your preferences, you can set up your default environment to show what libraries you want to have core loaded. You can load ISLR2, CRAN, and MASS, so you don't have to worry about them. Or the alternative is you just make a script that's your load script,
Right.
and it has those three libraries at the top of it and heads whatever files you're looking for. So you can automate that. Matter of fact, you can even build that as a function
Right.
to load all of your pre-existing data stuff. And that's what we used to have to do before we had fancy things like our desktop. Whenever I was starting with it, whenever you got a command line, okay, it popped up a command line box, and you had to type it all in. No UI, no IDE, it was just, the old hard school way.
I've noticed once I
Okay.
downloaded it, it seems to keep checked each time I go back into it.
Okay, good. Well, I was just wondering if that was happening now or not, but it used to be that it was a little flexible as to whether or not that worked. Everybody have questions on quadratic? I don't really expect you to memorize this formula, so if this is something you don't get in deep detail, obviously write it down in your notes, right, just to be able to have kind of an understanding of what it is. Because I think we'll first notice this delta, right? Anytime you see this delta, we're going to know it's a discriminant, right? We don't really use it for anything else right now. And as I said beforehand, it's kind of this weird, like, threshold/impulse function characteristic. That's the reason why earlier when you said threshold, it's like, yeah, you are moving the threshold, but that's the threshold, right? That in and of itself. I'm talking about when we get in and we assign weights, we're actually over here. We're changing values inside the system that force the threshold to be adjusted. Because what is this? This is generative. we don't actually tell the system what this value is, but we can tell it what these values are, and we can even weight these values, right? We can weight pi, we can weight log k for distribution characteristics, and as a result, what happens to delta? It changes, it moves around. So we can modify stuff inside the system. That is what we call a penalty or loss metric. Those are two terminologies I do want you guys to understand. A loss-driven metric is actually relatively common within the publication space for machine learning. If you see loss metric, those are people who are talking about attempting to minimize lost cases, right? You want to minimize your loss, which is the most costly, right? Cost is loss. So we utilize that term. We say we're going to cost factor, but we also say loss metrics or loss association. So loss minimization is what we actually are doing whenever we're doing most of the iterative development of attempting to optimize the value of the delta. So we're going to change some weights of some values in this system in order to try to determine the optimal outcomes we were looking at beforehand. All right, we've already talked about this across the way. Right, naive Bayes, and we'll look at naive Bayes real quick, and then we'll go to that for a second. Naive Bayes says that the discriminant for some system is going to be the log of the density prior, right? So the prior case. So it says essentially the systematic likelihood times the relative density of each element for each relevant feature of the system. This one's a little weird. Naive Bayesian mechanisms can only operate with effectively binary inputs. They only output the values between 0 and 1 for a likelihood perspective. So you can't create a high dimensionality Bayesian output. But what you can do is you can say the likelihood of being a member of a characteristic is the result of, or the product of, several individual Bayesian likelihoods multiplied together, right? So the likelihood of this being in class A based upon feature 1, likelihood of being in class A based upon feature 2, likelihood of class A being feature 3, the likelihood of class A is what? 1, 2, 3 multiplied together, right? So the collective, what we see up there again, we see our capital pi. Capital pi is the cumulative product, cum prod. So it says each of the individual likelihoods gets its own relative classifier. It's its own little Bayesian, okay? Its own little Bayesian is just a ratio. A priori times likelihood density over prior. Everybody gets one. Everybody, every feature gets one. Okay, the reason why I say it's not class, every feature gets one. Every relative class will be output based upon that system too. So this system gets inordinately complex in the effect that we can use it for assigning multivariate methodologies, and it has good operability for large P when n is low. But it is, how to say this? It's computationally expensive. One, to train it, and two, to be able to operate it overall. This system down here, this version of it down here is, in my perspective, a little bit inordinately complex. All this is a re-expression of the alpha of above here, right? So the log element in here has been taken out and expanded. So we just expand the summation. If we know this is density, and we know this as prior likelihood, right? Then we say prior likelihood times the summation of all relative densities for each of the features in that class grouping. We're going to end up with the log likelihood of the product of all densities. This says, when I look at it in this angle, it seems like an A. If I look at it from this angle, it also looks like an A. If I look at it in this angle, it looks slightly like a C, right? If I look at this angle, A, look at this angle, oh, it's a B, okay? What do we do then? Multiply all of them together, and we get one likelihood that combines or fuses together multiple different perspectives. multiple different angles of projecting the multi-dimensional space that is our feature space. So by flattening it into a bunch of two-dimensional views of that space, I can create very simple classifiers, naive based. We say they're naive because of the fact that what? They don't really understand anything outside of their own unique, discrete understanding of the space. So the naivety of that system means they're uninformed by anything that's adjacent to them. So each individual feature has its own class likelihood, and then the cumulative product of that system is seen as the composite likelihood, the chain of probabilistic sequencing that's creating the estimate that we're provided with here. Okay, we talked about logistic regression for multiple classes. Two-class problem is just a natural extension. We are going to take ratios of log likelihood, and then we're going to do this for each individual class. We say that so long as it has a standardized logistic regression form, we can have a chain logistic regression, but instead of it being a product relationship, it's a summational relationship because each one is a localized estimate characteristic. So localized regression, or localized logistic regression, uses log likelihood based upon characteristic discriminant learning. And LDA utilizes the full log likelihood, or full likelihood space, a priori, right? So it says it is known as generative learning, or it is a generative function. I've mentioned that terminology before. It's generative because it is based upon a probability function that is in fact derived from the data points. But since the data points are actually baked in to the function, this probability density ratio, right, the continuous form of the operation, the linear discriminant algorithm operator is not technically totally discriminative learning. It's going to be generative learning. We now have a distribution estimate, and we're going to be making an estimate based upon that estimate. We're actually 2 full steps away from the data points themselves. So in order to be able to modify the way the system operates, we actually have to modify the assumptions of the density model. So the Gaussian, we have to modify the Gaussians, those probability density function characteristics that have been generated from the data in order to modify the output of the LDA. As I said beforehand, LDA is that delta. I modify it by changing its assumptions about the underlying distribution of the data. All right, as it says, despite its differences, results are often very similar. All right, I want to go ahead and get to the other section. I mentioned this before. Logistic is popular when k equals 2. Logistic is popular for what? Binary. LDA is useful when n is small and classes are well separated, largely because of the fact that logistic falls apart when the classes are too well separated, or whenever there are not sufficient samples to be able to characterize the localization. It is also much better and much more stable than logistic or even naive Bayes when k operations are greater than 2, right? So whenever you have more than 2 classes, LDA operates better. Naive Bayes is good whenever p is very, very large because it's not actually susceptible to the curse of dimensionality. This is a weird consequence of the way Bayes works. Bayes works with huge p. Now the relative accuracy of it is different. It is less than what we would see in normal circumstances when p is huge, but it may be the only way to create a classifier that works with high dimensionality feature vectors. Yes?
Just for clarification, that p is referring to p-value, right? No, okay. I don't want to get them confused.
P-value is a capital P.
P-value is a capital.
Predictor. When you see lowercase p, think predictor, okay? People have had problems with this in the past. N, lowercase n, what is that? Number of samples. Lowercase p, the number of features, right? Predictors. Predictor, think predictor. Okay, I don't use predictor very often because I don't like the word, but because features is much more common in my space, typically. We say it is a feature of the thing. I worked a lot in image processing, and so visual feature is more common, so I tend to use that word more. But I do try to use predictor every now and again, just to have you guys not reminded, but P is predictor. So it says predictor is what? Every time I add a new predictor, I have a new dimension to the multi-dimensional space, the sort of cluster, right? Starts off XY, what is that? That's a 2D plot. XYZ, 3D plot. XYZ alpha, 4D plot. XYZ alpha beta, 5D plot, okay? Every single one of those is effectively a new P. It is a new predictor. It can be correlated between the input and the output. And if we have a high dimensional space, right, we see how the clusters, each one of these is like a little cloud in those high dimensionality spaces. They're all associated with one another relative to those feature characteristics. Classification attempts to define surfaces that transect those spaces and create boundaries, discriminants that allow us to be able to tell those clouds apart from one another. If you can flatten those in naive Bayes, you end up with a whole bunch of individual 2D images, each one taken from a different perspective of that space, and each one giving you sort of a composite, right? You guys ever seen the algorithms that are able to put together 3D models from taking multiple images from different angles? This is a bit like how naive Bayes does it, except it's taking pictures of the data set, right? It's taking pictures of the clusters. It's saying, well, relative to this angle, it's like this. Relative to this angle, it's like this, right? And the only thing I need to know is the product of those two likelihoods in order to define one global likelihood. However, what happens if even one feature is interdependent on another feature? Now the whole thing's out of balance. The whole thing's out of whack, okay? So naive Bayes will has its issues. It works incredibly well for a large P that other systems will not work for, but it's a very interesting, it's probably one of the most primitive ways of looking at a data model. It's primitive because of the fact that you end up with what? For P features, you have how many models? P models. P models for P predictors. Computational complexity goes through the roof in a linear fashion in the perspective of not only compute time, but in the production of each of those models. Now, like I said, some other systems where when you run through them, LDA is very, we're not gonna get a chance to go on fly, so. LDA is very front-heavy. We have to spend all of our time computing what? We have to compute standard deviations, means, we have to compute the density function estimate. So that initial investment of processing through all the data to get our distributions for each one is time intensive. After we're done with that, we don't have to mess with individual data points anymore. We can just now rescale the characteristics of the generated distributions in order to be able to optimize the classifier output, be able to optimize the discriminant placement. So that actually saves a lot of time. You do all the work up front, and then later on you don't have to mess with it. Naive Bayes, change one thing and you have to compute every factor for that entire set of information. Because how does it work? Everything summated together, everything else summated together, however everything else summated together. It's like you have to recompute the entire framework if you change even one point in the system. So it's a challenge in that effect. We're going to talk about next, so just to look ahead real quick, we're not going to look actually because I'm out of time, but we're going to look next at a process that we call folding, right? So we're going to talk about cross-validation and K-folding. That's where we're going to break up our data into little clusters where everybody gets to take turns being the training and the testing. Okay? That allows us to overcome some of the limitations of the data modeling we were doing previously. And then we're going to start talking about feature selection characteristics where we're determining which features we're keeping, which ones we're getting rid of. So Friday we'll start into that. Probably Friday and then Monday's material will be all the material that's going to be covered. So whatever I can get done on those 2 days will make the difference of what our midterm exam will be. Right now, this is obviously tentative, could be pushed, but right now we're planning on doing the exam on Friday of next week. Okay, so week 9, Friday, we're going to be pushing into that. Is it week 9 or week 8? What's week 7?
Week 7 this week.
Week 7?
So week 8-ish.
The 2 weeks then. Maybe it's Thursday after next. Let me look and see. I may be wrong, but I'm thinking it's going to be next Friday, okay?
Okay.
If it isn't, then it's the Friday after that or the Monday after that, all right? I'll let you know I will let you know definitively at least 1 week in advance, but right now, just start preparing. You've got 4 chapters worth of material to go through. You know, anything that's on that introduction that we discussed can be on there too, so keep those in mind. So get busy, it's a lot of material, it's a lot of stuff to know and cover. Focus mainly on conceptual characteristics, definitions, and understanding the models themselves, and I will give you some material along the way, so don't panic, okay? Talk to you guys on Friday.
Thank you. Oh, are you still doing Panopto on Friday?
Isn't that another slide?
Yes. Okay. so-
Yeah, I'll post it over remote Friday, because I had a lecture, I'm giving a guest lecture in another course overlaps this week.
Thank you.
So, yeah, thank you.
So the next Friday we are not going to come.
Not next Friday, this Friday,
This Friday.
this Friday.
You
We
can
will
come.
actually be here Friday, I forgot.
You can come, but he might not be, right?
No, I definitely won't be here, I'll be in classroom 104, so. Yeah, I forgot, I mentioned it so that you guys, so that you would be able to remind me, I appreciate it. There is a new course, they started this last semester, it's, what is it? Biomedical,
Yeah.
instrumentation, I believe, or no, that's the other one, right? It's biomedical sciences survey course. So they're starting a new undergraduate biomedical sciences survey class, and that's going to be, I'm giving a lecture in there.
No, this
on,
Friday we are going to have class.
EEG, molecular submolecular brain.
So this Friday we are going to have class. The next Friday we will not have
Introductory
with him.
Huh?
So is that like?
But the next Friday I have question like next Friday is going to have a midterm.
It's the, like, one of the very first symposium classes where they're having like cluster learning. So they have everybody that's involved in that program is in that class. And as a result, it's like they're bringing in instructors with, you know, different interests and experiences. And I've done a lot with EG, so they said, yeah, come on in and give a lecture on your experience, talk about the topics. It's gonna be basics plus some, you know, tips and tricks, limitations, emerging fields type stuff, kind of an overall survey of the topic. I'm gonna see if I can get it recorded for you, yeah, and I'll upload it in here because it may have some data science and data processing characteristics as well. So if you guys are interested,
I was just getting ready to ask if,
Yeah,
I don't know
sure.
if it's still possible.
I'll try to see. I have to ask is whether or not it will be the case. I'll ask Dr. Blumker whether or not we have room in the classroom space. So if we don't, then I'll have to go ahead and have you guys remote. But I might be able to have room for a few of you guys. I'll let you know in advance if I do. I'll put it out, and whoever kind of first come, first serve, if I have a few that want to come over. So, yeah.
Appreciate it.
Yeah. See you next week.
Yeah, indeed.
Yeah, I'm gonna.
I'm not going to be here day after tomorrow, Friday, right? The 6th Friday is when I'm giving my guest lecture.
Okay.
John reminded me, so I mentioned it on Monday, and then he reminded me again, because I knew if I didn't mention it on Monday, I would forget. So I just automatically say when the next class period is. I'll put a note out on Canvas, like, as soon as
Next
I
Friday.
want to
Minute.
do it now, but
The day.
that way we don't have any confusion, but I will actually be recording a Panopto lecture in advance for the introduction to cross-validation, so you guys will have that to watch if you're not here. Yeah. Thank you. Appreciate y'all being here.
Huh?
We will give analysis.
So, couple of
logistic regression.
course-related questions.
After we get some values
So,
like intercept and
You
something like
mentioned
coefficient and so on.
first,
Right?
possibility of
I
like,
haven't
one of you
go
guys
through
would
it.
be
If I go through it,
pretty,
Yeah,
I can tell you.
understand all
I
that.
didn't. I was using. I was using Python. Then I shifted to
I
R.
can't do it.
It's taking me
Can't
time,
do
but
it.
I will
It
finish
doesn't
it.
work.
There's no way that you
Did I
can.
It
ask?
doesn't work. I can't do it.
Do I have to
Okay.
have some
I can show you
reaction?
some
Here we get
things
quotient and
in
intercept, right?
non-Euclidean
Yeah.
space,
It will have some
People
range
have
right
done some
less
stuff
than
with
this value
VR.
means
Yes.
it's good and
but it's
like that.
so disconcerting
I
that I
want to
wouldn't
know
recommend
like
it.
for logistic
It's
regression,
weird.
how
It's
much
literally
intercept and
messes with your
quotient
head.
will
That's
be.
right.
Okay, so that, have you ever seen the movie Donnie Darko?
such that it will, you know,
Darko, I remember that,
Yeah.
Can you tell?
So Donnie
That
Darko, there's
intercept
a scene in
and,
Donnie Darko
intercept
where
values will
he
get right
breaks into
Yeah.
the fourth
Just
dimension.
So
look well.
I guess
you better ask him because
Say,
he can.
he
tell you,
actually
because
breaks
it
into the
might
fifth
be-
dimension, because we are four-dimensional entities.
Yeah.
You have to be one dimension above it to observe it.
Oh, okay.